Hi, thanks for joining me today. I'm going to talk briefly about response function analysis, which is a common multivariate technique used in dendrochronology, but may be useful for other studies as well. So this was introduced in the field by Fritz in 1971, and it aims to explore the relationship between intercorrelated predictable variables, in this case climate variables, temperature and precipitation, and response variable, which is tree rings in this case, but it could be others. And it helps uncover complex patterns related to tree growth. So this is an important aspect because tree growth is affected by a lot of things. And for trees specifically, a lot of those variables are correlated to each other, right? And you can see here, for example, in this example, when you use multiple variables, some of them might be highly correlated, like variables 1 and 3. And untangling the effects of individual variables can be a bit hard. So one way to go around this, what proposed by Fritz, was to use regression, do the regression of the principal components instead of the original variables. So you take your tree rings, your millimeters, and regress those on the individual principal components. And this would get rid of those correlation problems, right? So to understand a bit more of the issues that are faced and how this technique works, we need to learn about what we're trying to achieve. So basically, in dendrochronology, you're trying to model tree growth as a function of climate. Tree growth is we use the proxy of ring width, right? So basically, you're measuring the width from one boundary here to the next. And then you can actually plot that in a time series, like you see in this graph. Right? For climate, you have mostly temperature and precipitation as the main drivers. There's a bunch of other things, of course, but temperature and precipitations are kind of like at the top of the chain of events. And those can also be plotted as time series as well. Right? So for example, precipitation, you can have total annual precipitation, or mean annual temperature. So what you could do is that since you have specific rings assigned to specific years, you can do the same. You can just do a correlation between the two and see how much that helps you understand. However, this is not the best way to do it because you're losing a lot of information. So trees, they don't grow in a uniform manner throughout the year. They actually vary a lot. So there are parts of the year that they are dormant, some parts that are growing more. Actually, sometimes even like single day events like defoliations or frosts can affect the tree growth for the entire year. So when you do this, you're losing a lot of information. So what's usually done is that you actually break down your precipitation values or the temperature to monthly data. And you do the same analysis. So you do, let's see how much January affects the growth, let's see how much February affects the growth in December, so on. You can do the same for temperature, right? And you can see that the values are a bit different from the overall correlation. In case of precipitation, right, because you're partitioning precipitation, you can see that the value decreases, but for temperature, for example, you can see how April increased a lot the strength of the correlation. Right, so you have a 0.2 when you had basically 0. So this shows us that there's some structure on how tree species respond throughout the year. And you can actually go ahead and plot those correlation coefficients and see how the growth changes from month to month for the individual variables. Right, so you can see that from May to September, the species is growing well and responding well to increases in precipitation, and for the same period it's not responding well for temperature, right? So maybe it's a bit limited in water. So that gives you some insights already. However, there are some fundamental issues associated with this kind of analysis. So when we're trying to explain total variance of tree growth using multiple variables that are correlated to each other, right? It gets really hard to, again, untangle those patterns. You cannot say that December is really important for the plant individually, right? Because what happened in November may have affected December, and what happened in October may affect November. So you can see how it gets really hard. You also have the problem that precipitation and temperature are intercorrelated, but from this graph we're actually analyzed them as if they were independent, right? But they're actually complementing. they do affect each other, and this is important because we're not taking that into account. It would be like saying not taking into consideration this overlap here in various explain between them, right? So you can say that December is really important for precipitation and December is really important for temperature, but when in reality it's just this part here that actually corresponds with how important this variable is. So this is really hard. Also, there's the added issue that if you're trying to do any statistical task to see how significant your estimations are, you are doing 24 tasks in this case, and this can greatly inflate your experiment-wise error, right? Because the chances of finding a significant month just by random chance increase a lot. You could adjust this, right, to reduce your chances of finding a false positive, but you usually also reduce the power of detecting that signal as well. So an example, an a priori confidence interval would have several variables deemed as significant, and if you do an a posteriori, like an adjusted, only December for precipitation would actually be significant. Does that mean that only December is important? No, right? But that's what it's kind of implies. So to really understand that structure and get some reliable statistics out of it, Fritz then thought about using the regression and principal components. So let's do a quick recap on what principal component is, right? So it's basically a linear combination of original variables. So you will find a line of best fit, right? And you can, based on that, you can find that slope or that ratio or proportion between the two variables. That line actually contains information for both variables, based on those coefficients that we just found. And this is what principal component does. It tries to find the line that best explain the data set and gives you the coefficients for that. However, there's some residual errors that you can see on the dashed lines. So the analysis do this for, it finds multiple principal components, and the important aspect here is that those principal components are all orthogonal to each other, so they're not correlated, right? So if the principal components are not correlated, you can actually use them as variables and not have the problems of correlation that we just talked about with January, February, the time series correlation, the autocorrelation, and the intercorrelation between precipitation and temperature. Now that's really interesting because you are actually assessing the individual effects of the variables. Right? Usually we would plot, the principal components 1 and 2, which are the ones that explain most of the variance, and analyze this in scores. But we're actually going to do something a bit different here. So it's a little bit less intuitive, but it does make sense and it does yield interesting results. So the step-by-step on how this is calculated is basically you wrangle your data, you put your variables as columns, right? So the individual month. And then you perform your principal component analysis. You can extract the loadings, which are your vectors, right? So the weights that form, the principal components, and the scores. And you're gonna do a selection of the principal components, right? Because similarly to what we do when you're trying to visualize principal components, right? When you're doing only 1 and 2, usually they account for the most variance. And the ones that do not account for a lot of variance, they usually can be regarded as errors, right? The same is for true rates, right? So those principal components that do not have high eigenvalues, they are simply, you can regard them simply as errors. So there are different criteria on how you select them, but the programs usually have a standard format, which is good. Alrighty. So you then remove the unimportant pieces, and then you get the scores for the principal components you selected, right? So if you had 24, because you have 24 variables, you're going to have 24 principal components. You can remove, the last 2 or 4 or more, and use only the ones that explain more variance. So when you do this, you're actually increasing your chances of getting, extracting a signal, a climate signal. Then, when you do this regression, you're going to get a coefficient for each principal component, right? So principal components, they do not mean anything for us, right? So sometimes you can find a structure that makes sense, but you cannot say, increase principal component 1 by X, and then your tree will grow better, right? So that doesn't make sense. So the last step is to actually use those coefficients, right, of principal components, and revert them to actual, coefficients related to the variables that we are interested in, right? You do this by multiplying those coefficients by the original PC loadings, and then you end up with a table like this, which are your response coefficients. So this response coefficients represents how much each of those variables individually contribute to tree growth. Well, that's really interesting, and that's something you don't have with simple correlations. So again, you can plot that as bars, for example, like we did before, or sometimes as points, as we're going to see. So I just wanted to mention that because that's how you're going to see in the lab. So the next thing to do is to test the reliability of those response function coefficients, right? We did so much transformation, so we want to know that they actually represent, they can actually, predict growth as best as possible. So what we do all the steps that I mentioned, and you get your, set of coefficients, but you're only going to do that for part of your data set. So in this example, we have over 500 years of data, and then you're going to select only the first 400 years, right? So let's say 75%. This will be your calibration part of the data set. So you're going to do this analysis with your original variables, and you're going to end up with your response coefficients. Now you're going to take those response coefficients, right, because they help you predict growth, and you're going to let me get this table, and you're going to see how well they predict growth. So you apply the function, get the predicted, tree rings that you would expect, and you compare that to the actual observed values. So then the correlation here, you have a measure of strength of how well your, data set is performing, and this helps you predict growth over independent years, right? Not only to that data set that you're working on. It's the same as machine learning, training and I forgot the other name. It's like cross-validation. Then you're going to do that again, but with a different part of the data set as calibration, a different part as validation. So in fact, you're going to do this 50 times, and then you're going to get 50 regression coefficients for each of your variables, like precipitation of January, February, March, and so on. And you're also going to get 50 correlations between, predicted and observed. So with that, you can actually build confidence intervals and see how well your model actually predicts tree growth independent, right? Independent data sets. So you can plot your coefficients, and this is what you're going to see, right? Because now you can calculate confidence intervals, and this is the output of the program you can use in the lab today. So the dots mean that the mean response coefficient that you found, and the whiskers, the top and the bottom, the confidence intervals. Roughly, if the whiskers are crossing the 0, then you would not say that that is a significant month or a significant variable, right? However, if they do not cross 0, then you can say with more certainty that those are important months, right? Because no matter how, basically you can think about this, like no matter how you scramble the data, every time temperature increases in April, growth decreases. Or every time precipitation increases in August, then growth increases, right? It can be, by 40%, but it can be by 10%. We don't know exactly, but you know how much, you know that it will affect. So that's really interesting. So just some general points here of what I explained. Yeah, and this can help you, find some structure in the data. You don't need to look only at, significant months. You can actually look at the general structure, right? So sometimes you clearly see that during the summer, precipitation, all the values are tending to be positive. So that's a good indication as well, right? So this tree does not like high temperatures in April, as you can see here, but it grows better if temperatures in May are higher, right? So those are good insights and help you even predict how a species, for example, will do in future climates as well. So now we can move to our lab. You're going to use tree clean to do that response function analysis, and we're going to use tidyverse just for the wrangling of the data. So you can click here or just find it on the website. Thank you.